Hi guys, welcome back to the Think class of operating system concepts, and here we are going to discuss something about process synchronization, and here I am going to provide you some kind of advanced theoretical concept. I already have given you the process synchronization basic concepts before, so here we have some kind of advanced theoretical concepts in process synchronization. And before going to the topic, and let's go to the traditional session of humor. So, and today I have brought you a difference between girls' diary versus boys' diary. So, what is the like girls' diary versus boys' diary? So, in girls' diary, what we really found is something like this. He was quiet today. I asked if it's my fault. He did nothing. I said I love you. Okay, but he smiled sadly. I cried all the night. This is some kind of sentence that you find in girls' diary. Whereas in the boys' diary, what is found is like, shit, Liverpool lost the match. Okay, some kind of sentence like this. Okay, now let's begin the session. Okay, so what is a round robin scheduling? In round robin scheduling, what is done is that the process are dispatched in a FIFO manner, that is first in first out. Okay, but are given a limited amount of CPU time. That is, the time is mostly measured in time slice or a quantum. That is very small unit of time. I mean, you can also say smallest unit of time. The process is allocated for a particular job. So if a process do not complete before its CPU time expires, the CPU is preempted and given to the next process waiting in a queue. The preempted process is then placed at the back of the ready list. This means like process has to complete the task in the given time slice. And in this time slice the process is allocated. But if the process is not able to finish the job in that allocated time slice, then what happens is like the preemption occurs and the process is kept in back of the ready list. So it is it's kept in the waiting list. Okay, round robin scheduling is preemptive. That means it goes to the end of the time slice, and therefore it's very effective in time sharing environment in which the system needs to guarantee reasonable response time for interactive users. That means, for example, if you are like hitting a key and you are like, if the process is asking for some user to enter his name or surname or enter his password before locking on inside the computer, then this is very effective, right? Because the process is not allocated for every time for all the moment. It is allocated for some certain time slice. Then it waits for in the ready queue, right? Okay, this was just about the round robin like scheduling. Now let's go to the next question, and the next question is like, what's the difference between kernel stack and user stack then? In kernel stack can be only accessed in kernel mode and has the privileges to access the underlying hardware, while the user mode stack do not have the privileges to access this kind of underlying hardware. This user stack just act as an interface to communicate between the user and the kernel. Okay, And when a system call is issued, say to open a file. For example, if you want to open a file, if a user want to open the file, then he he has to ask the kernel to open the file. So he has to communicate. So for this communication purpose, some particular syntax are provided, and user uses this particular syntax to communicate with the kernel, and kernel allocates the kernel stack to communicate with the particular hardware by using the IO interface. And the process switches to kernel mode stack because file system information can only be accessed in privileged mode. So to open the file, the process switches to the kernel mode stack because file information, as I already told you, all the privileged information are already provided in a kernel mode only. And what is the main reason behind separating this user stack and kernel stack? The main reason is to protect the kernel data structure from becoming inconsistent. That means tasks that are privileges are only used or shared by kernel stack, whereas all the other tasks are done in a user form, in a user stack. Also, you can see the call interface, system call interfaces here, and the stack grows. Okay, it's just increasing here. Like you can see here, the parameters of main argc argv are done here. We call the main method, okay, the address to the frame, and local variables like old for ft, new ft file directory is also here. Parameters to copy, return, okay, all these things are done here. We can check out through this example here, the copy.c example. It is simple file copy example, which is going to show you the difference between and in which stack which is called, okay, which function is called. All the parameters that we have assigned here, like the main function, it's called here in this argc and rv, okay, argument counter and argument values or variables as parameter are using the user stack, right? You can also call the main method here, the frame, the main, like you can see out the open source file in read-only mode. Okay, this variable, the file descriptor variables, okay, all are called in this user stack. Okay, the call to copy, okay, the copy function, you can see out here. Okay, the call to copy, address of the frame, variables, okay, and you write function, and the real task, okay, this is just a syntax just to communicate with the kernel, and the real task is performed in the kernel stack. The real the system call interface, okay, is called here. System call is called, which will then directly communicate with the IO interface. Then the IO interface communicate with the particular device drivers, and the job is performed, right? So this is the way of how there is a difference between user stack and kernel stack. Now let's go to the next question, and in the next question we can see is, what is event flag? Event flag is something like a process synchronization primitive in an operating system, and a process is synchronized by means of signals. So the signals are like lock and unlock. Some particular signal there you can find in Unix are lock and unlock. And lock, what it performs is some similar actions like sleeping, whereas unlock, it performs the similar actions like wake up call. Okay, now the next question is like, what is a semaphore variables then? A semaphore is somehow like an integer variable, but it is special. What is special is like like its operations like increment and decrement are guaranteed to be automated. Okay, so you have to understand like uh, that automate operations means some operations which cannot be further divided into another operations. So these atomic operations are like a unit of operations and they cannot be further divided. So like the operations like increment and decrement, like you cannot say that they are just the increment operation is just going halfway through it. So the whenever you call the increment operation, that means increment is done and it is atomic operations. This kind of operations like is performed, and so we can increment and decrement the semaphore for multiple threads without interference. And the idea behind this is like we can increment and decrement the semaphore for multiple threads without interference, right? So by convention, there are some key notes to understand in the semaphore. It's like semaphore is 0, that means it is locked or it is in use. Whereas if a semaphore is positive, having any positive values, then it indicates that the semaphore is very available. And the semaphore can never have a negative value. This is the most important concept you have to understand. It's like semaphore is never negative. And a semaphore can be defined in such kind of structure. So you can define a semaphore in such kind of structure, passing the parameters for lock, counter, the pointer to the process header. Okay. And lastly, you have to also understand two key operations, kernel operations, okay, for semaphore, okay, which are used in the semaphore method. Two kernel operations are disable semaphore and enable semaphore. In disable, what we do is like we suspend the issuing process and append it to the semaphore list. Okay, we are suspending, disabling means we are suspending the issuing process and we are appending it to the semaphore list. So it goes to the semaphore list. Whereas in the enable kernel operation, we move the first process block in the semaphore. Okay, move the first process blocked in the semaphore to the ready list. Okay, this was just about the semaphore variable. Now what are the methods for semaphore variable? I already noted and told you that there are two kind of methods including two primitives in semaphore. There are wait method and a signal method. And what is the internal structure of this wait and signal is provided here. First, what is done is we initialize the counter for the semaphore by calling this init method, and also you have to be careful that the counter must be always greater than or equals to 0, as noted that semaphore can never be a negative value. And inside the wait method, what is done is like we decrement the counter and we check if the counter is less than 0, that is not possible, and if it is less than 0, then we immediately disable the semaphore. This kernel like operation is called from this method, okay, wait method. If you want, like you are using a signal method, then what is done is we call a kernel operation, that is enable kernel operation, which enables and which moves the first process block in a semaphore list to the ready list. Right here we increment the counter, then we check if the counter is less than or equal to 0. Then similarly, if the counter is less than or equal to 0, then we enable it. Okay. Now how do we synchronize by means of semaphore then? We follow the following steps to synchronize by means of semaphore. First, we need to declare the semaphore variable by using this type define. Okay, we define the structure for the semaphore. Then we use the method wait. Okay, when the train must be wait on the semaphore, and we also use the method signal to release the waiting thread. Okay, now you can check out the in the following diagram how it is working. Is like how this method works is like the statement says B must be executed in process Pk only after A has been executed by process Pj. And you first initialize the semaphore variable, that is 0. This also means pure synchronization. Okay, now what is done is like A, after it goes to the critical region and it finishes the job, signals the semaphore, and B is still waiting for A to signal the semaphore, and when it the A signal the semaphore, it captures the signal semaphore, then B start executing. So this is the way how it works. Okay, and these are two different processes, Pi and Pj. So in Pi process A is signaling, whereas Pk process B is waiting and then completing its job, and they are all just doing it just for the semaphore, and this helps in the synchronization among process I and process Pk, process Pi and process Pk, right? So how, by using the semaphore, we can implement the co-begin and co-end block is in this precedence graph. You can see the process, right, from process P0 to process 1 to n, whereas lastly to process n plus 1. So how the co-begin and co-end block is implemented is like, first you initialize the two semaphores, that are semaphore 1 and semaphore 2, and they are initialized to 0. And in process 0, P0, what is happening is like, if you go and check out the body of the process P0, we just signal out to all the process, all the other process, child processes. The semaphore 1 we signal out from by using a loop from a condition with I like index is 1 to less than n, and signal out to all the other child processes. Whereas in the process, all these other processes, what it does, it just waits for this process P0 to signal out, and signal out the semaphore. It waits for the semaphore, then the body of Pi P1 starts, and in this body it signals out the other semaphore 2. Okay, all these processes, they just signal out the semaphore. And lastly, in the process Pn plus 1, what is done is in the process Pn plus 1 first waits for all the other these processes to signal out the semaphore 2, and first it waits, then the body of Pn plus 1 starts. Okay, so this is the idea. Okay, now how mutual exclusion is done with semaphore then? Similarly, as I have told you before, like mutual exclusion is done here in following way. First, we have to always initialize the mutual exclusion semaphore, and this is like initialized to 1. And in process Pi, what happens is like we first wait for this following semaphore, then it goes to the critical region, then the job is executed, and after the job is executed, the semaphore is signaled out by using this signal method. Okay, so the most important thing we have to be careful are these time dependent errors while using the semaphore to synchronize, and that is, if you go and check out here in process 1, okay, first so remember that the semaphore is initialized to 1. What is happening here is like it is first signaling out the semaphore, and lastly it is performing the job in this process 1, like critical region of process 1, and waiting for the semaphore. And this is totally not a good way of using semaphore, because it is just creating some kind of error, okay, long time waiting kind of situation where the process 1 will be still waiting and the other processes will also be still waiting. Like if process 2 is waiting for the semaphore for process 1 to signal out the semaphore, right? And but still it is waiting for semaphore 1, and they all are also still waiting for semaphore 1. So this will create some kind of time delay. So these are some kind of time dependent error that will cause when we use this semaphore in a wrong way, right? Also the second condition that must be avoided is like we cannot wait for a semaphore, go to the critical region and still wait for the respective semaphore. This kind of conditions must be avoided. The only good condition is this one, like we wait for the semaphore, we perform the job in the critical, we go to the critical region and perform the job, then we signal out the semaphore. This is the right way of performing the semaphore, using the semaphore to perform the job. Now the key concept about what are deadlock and starvation and how are they occurred is like deadlock is occurred when 2 or more processes wait indefinitely for an event that can be done by only one blocked process. Okay, that is because of only one blocked process. So if you check out the process, like first you see that it's the semaphore are initialized to 1, semaphore S is initialized to 1, whereas semaphore Q is initialized to 1, and in process what is happening is like it's waiting for semaphore S, and still in the second time it is waiting for semaphore Q, whereas what is it doing is signaling out semaphore Q and it's signaling out semaphore S. But process 1, the another process is waiting for semaphore Q, okay, and also it's waiting for semaphore S. So such kind of long-term waiting is occurred here, okay, and this is signaling out semaphore Q, whereas this process is like waiting for semaphore S, right? And also you can check out like this process is signaling out semaphore S, whereas this process is also waiting for semaphore Q. So there is some kind of deadlock situation, okay. Process 1 is waiting for something that is not signaled by process 1, whereas process 1 is waiting something that is not signaled by process 0 in a particular respective order. Okay, so such kind of deadlock condition is occurred here. And similarly for starvation, the same situation can be seen here. Like deadlock situation occurs when a process keeps on waiting and like there is no signal, and no semaphore is signaled to the respective process that is waiting for some particular semaphore. So long-term wait occurs here, and this causes starvation to the particular process because it cannot perform the task. Okay. Okay, so like and you can see like how to resolve the producer and consumer problem using semaphore diagram. Okay, this was like the last part. In the last part we see like to solve the producer and consumer problem, and like in the also in the previous lecture I discussed about how to solve the producer and consumer problem, but this time we are just using the semaphore to solve the producer and consumer problem. And if you go and check out, like first what we have to always do is we have to access or define the access function to the common buffer. So that is the common buffer situation. What we do is we like define the message. Okay, the size is the maximum size is max, whereas we also define the input and output variables, and in this input and output variables is initialized by this function, init function, and they are initialized to 0 respectively. Whereas in the enter function, what is done is like we enter the message, like we produce the message. Whereas in the remove function, what we do is we consume the message by the consumer. Okay, so now let's first check for a particular single producer or consumer situation. Okay, how can we solve by semaphore using the single producer and consumer situation? For single producer and consumer situation, what we do is we first initialize the semaphore to full to 0, and we also initialize the empty to maximum. What is done is like the producer, in the producer block, the message is generated, the message M, where like there is M messages, and while the condition is true, what we do is we produce the message, okay, by using the following we start producing the message. Then what we do is like this is like we use the wait method to wait for the semaphore, the empty semaphore. We wait for the empty semaphore, and we are initialize. Okay, we initialize empty semaphore to maximum, okay, max value, and then after waiting for this semaphore, all this semaphore, we start producing the messages. Waiting for the semaphore, we produce the message. Then after producing all the messages and wait, like the waiting completes for all these values, we signal out the full semaphore, which is initialized to 0. So full is signaled. Okay, so in this consumer block, what it does is like while the condition is true forever, we wait for this producer to signal this semaphore full, and then we remove the message, like we consume the message, then we signal out that we consume the message to the producer as like we signal out the empty. Then this is the producer gets the semaphore, is waiting for the semaphore, it gets the semaphore, and then it start producing. Then again after producing, it signals out the full semaphore. So similarly it goes on. Okay, it keeps on going forever. So this is the situation just for single producer or consumer. But what about if there are multiple processor, like multiple processor for producer and consumers, and how can this be solved by using the semaphore? Is like we just have to do is everything is similar. We have to initialize these two semaphore for full and empty. Whereas in extra, what we do is we initialize also this mutual exclusion semaphore. Okay, in this mutual exclusion semaphore, we initialize the mutual exclusion semaphore for producer as 1, whereas also we initialize the mutual exclusion semaphore for C as a 1. Then in producer block, what we do is we have to just produce the message and wait for this empty semaphore, and then what again we have to wait is for wait for the mutual exclusion of producer semaphore. That means no other producer is producing while this producer is producing, right? Then you start entering the producing the message, and then you signal out for after the message is produced, you signal out another producer to produce the message, and you also signal out to the consumer that also that you have produced the message. Then in the consumer block, you wait for the producer to signal out full semaphore. Okay, and after getting the full semaphore, it also still wait for the another consumer process that to okay, the mutual exclusion consumer semaphore to start consuming this process, that only this like particular consumer process is consuming the message, and similarly it also signal out that the another consumer process that it has consumed the message, and it signal out the semaphore, whereas also it signal out the producer to that it has consumed the message. So similarly it goes on, and mutual exclusion is occurs among producer consumer and also among producer and its respective another multiple producers, whereas also consumer and producer and the consumers with his respective consumers, right? So this is the way to solve producer and consumer problem by using semaphore. Okay, now thank you guys for listening this session, and hope I will continue in the upcoming session with the examples of all this implementation, and